Okay, hi everybody. Sorry that took a bit longer than I thought it would. So today I'm going to tell you a little bit about JavaScript under the hood. But before we get into it, I'm going to tell you a little bit about myself. So hi, I'm Ridhwana Khan. I'm a software developer, and I love software development because it helps me to make an impact to people's lives. I love building systems, and I love building systems that are useful to people, that people find intuitive, and that makes people's lives interesting and easier. I've co-founded a software development company called 01, and at 01 we build custom software dev for different clients within different markets, and we work with different software teams, and we really enjoy sort of integrating with different teams. I like speaking at events like this because I think it gives me a different perspective, and it allows me to meet people with different perspectives and to learn from other people, as well as to share my knowledge. So I do a couple of other things. I organize some meetups. I organize a meetup called Ladies.UX and another meetup called Women in Tech. And these meetups basically have the same goal. The goal is to promote diversity, to promote learning, and to promote building relationships with each other. The only difference between the two groups is one is in the user experience space and one is more in the tech space. I'm also a co-founder of a nonprofit organization called Kasimats. Kasimats is a program that runs in underdeveloped areas, and it's a program that teaches children to develop their skills in mathematics, to build their confidence in mathematics, and to increase their enjoyment of mathematics. Above all of that, I'm an extreme JavaScript enthusiast. I think that JavaScript is a fun and quirky and exceptionally powerful language that I absolutely have learned to love and sometimes hate. So I think we all can agree, we are at Jozi.JS. We can agree that JavaScript has become increasingly popular in the recent years. For the 6th year in a row, Stack Overflow has recorded JavaScript to be its top used language. So a whopping 69.8% of users actually use JavaScript. Another platform that has done some statistics is GitHub. GitHub says that out of all the pull requests that it has on its platform, especially the open source ones, JavaScript is the most used language on its platform, with 2.3 million pull requests open, which is carried out in JavaScript. GitHub also mentions that the different commits and pushes that happen to GitHub, 28% of them are JavaScript based. So looking at these stats, I get huge FOMO. I'm so overwhelmed at times. I think it brings all my insecurities to the forefront that I have to be at the top of my JavaScript game always, every day, all day. But it's difficult to stay at the top of my game, right? Look at that. In the past 3 years, I've used at least 6 of these frameworks. And that's a lot. There's a new kid on the block every single year. So JavaScript is used on the back end. It's used on the front end. So there's frameworks. So on the back end, we have Node.js. On the front end, we have things like React, Angular, Ember, all those cool kids. And then we have JavaScript we use in embedded devices. We use it in hybrid apps. And we use it on desktop apps like Electron. There are so many frameworks out there. But these frameworks and these libraries, they come and go. And it's difficult to stay on the top of your game. And it's difficult to remain relevant because there are so many. So I feel that by understanding the core JavaScript and then being able to apply that knowledge to the different frameworks, that's how I try to stay at the top of my game. So reflecting back to when I started my career, these terms were all thrown around, all around me. Things like call stack, asynchronous, concurrent, single-threaded, V8, non-blocking, event loops. It was crazy. I didn't know what any of those meant. And it didn't stop me from throwing it around as well. People would ask me, people would ask me, so I hear you do development. What kind of development do you do? And I'd go, I'd tell them what I work on, and they'd ask me, so what languages do you use? And I'd say, oh, I use JavaScript, that asynchronous, concurrent, non-blocking language. And I'd smile at them, just like, please don't ask me any more questions. Just the way I'm going to smile at you guys at the end of this talk. So I got through a lot of my initial development years without needing to know the nuts and bolts of JavaScript. I didn't really need to know how JavaScript actually impacted my applications because I was able to use these frameworks and just get up and running really quickly. I probably could have gone a couple of more years without knowing the nuts and bolts of JavaScript. But as you grow as a developer and as you become more experienced in the industry, you realize that it's important to understand the fundamentals. It's important to understand the mechanics of JavaScript and to have fine-grained control over certain things, especially when the application isn't your normal application. If you're building an application that's not following the norm, you want to be able to understand the mechanics to be able to proceed with using the language that you're using. I also want to be able to know that I can make better design decisions and architectural level decisions, as well as take into consideration performance and efficiency. And that all comes by knowing JavaScript a little bit better. Whilst it's possible to build large-scale applications without knowing the JavaScript engine under the hood, any car owner will tell you that they've at least lifted up the hood just once to look what's under. So by the end of the presentation, I'd like to get my hands greasy and tell you guys exactly what's under the JavaScript hood and how knowing each of these things allow you to write more optimized and efficient code. So let's talk about how JavaScript works under the hood. For the context of this talk, I'm going to talk about JavaScript in the web environment. So basically, this diagram represents all the moving parts in a JavaScript web application from the time we load a URL up until the time we close the page or close the application. So let's go through them. So the user interface. Almost everybody knows what a user interface is. The user interface is the part of the application where we see the buttons, where we're able to interact with some data, where we're able to see some sort of state. Then we have the data storage on the extreme right, and that's where we can persist local data, so things like for authentication, like cookies or browser caching. We also have the browser engine, and the browser engine acts as a middleman between the user interface and the rendering engine, and it also is responsible for communication with the data storage layer. Sometimes the browser actually has the browser engine and the rendering engine in one. The rendering engine is really interesting to me. I'm not actually going to cover it in this talk, but it's definitely on my list to talk about in the future. So the rendering engine will display your layout, your HTML, your CSS, your images, your PDFs. What it does is it takes your HTML and your CSS and it parses it into something called a DOM tree. Once the DOM tree is parsed, it then prints the layout to your interface on the browser. And the most exciting part for me of all, and what this entire talk will be about, is the JavaScript engine. So the JavaScript engine is specifically designed for speedy execution of applications. It is the technology that essentially executes your JavaScript code. Different browsers and technologies use different engines. And initially, a couple of years ago, this was a little strange to me. Because how are we running JavaScript code on different engines? But it's true, each browser has its own engine. So for instance, Firefox uses an engine called SpiderMonkey. Safari uses something called JavaScript Core. And the V8 engine, which is my personal favorite, is used by Google Chrome and Node.js. So I think it's important to realize that the end goal of what these engines do is all the same. They all want to be able to execute JavaScript code in the most efficient way possible. However, the way that they do it is slightly different. So the way that code may be interpreted and compiled on one engine may be slightly different to the way that it's compiled and interpreted on another engine. Also, the performance on each engine has a slight difference. But the purpose of this talk is not to go into detail around each engine, but rather to understand the context in which this engine is used and how we use it in the context of development. So in web development, we don't actually use the engine directly. Instead, we use the JavaScript runtime. I'm throwing all these terms at you, the JavaScript engine, the JavaScript runtime, but what are they actually? So essentially, the JavaScript engine works inside of an environment, which provides additional features to your scripts. So based on that definition that you see there, the JavaScript engine essentially translates your scripts into runnable machine code instructions so that it can be executed by the CPU of the host machine. The engine translates the scripts at runtime on the fly. Your code won't be compiled unless you run it. Whilst the JavaScript runtime provides your scripts with utility libraries which can be used during execution. It's your script that references these libraries. The engine itself does not depend on them. So essentially what that's saying is that the runtime provides you with all these scripts that you can use in order to run your application. And there's something really cool about that. So remember when I mentioned that the Node.js and Google Chrome run on the same JavaScript engine? It's because they actually have different JavaScript runtimes. So the Google Chrome browser, in its runtime, it has external scripts which it accesses via the web APIs. Whereas in the Node.js library, it uses sort of C libraries to ensure the threading is correct. So JavaScript engines can execute synchronous code and asynchronous code. So synchronous code is whereby the code is executed, and then it has to wait. A function is executed, and we have to wait for one function to execute before we can execute the next function. Whereas asynchronous code allows other code to execute or run, but it responds at a little bit of a later time. So we're going to talk about JavaScript in the context of synchronous functions, and then we're going to talk about it in an asynchronous environment. So when we're executing functions synchronously, there's only two things that you really need to take into consideration. The first thing is the memory heap, and the second thing is the call stack. So the memory heap is used for memory allocation and memory management. The call stack is a data structure that lives in virtual memory that records any function calls that occur. So let's go into detail about them. So the memory heap essentially performs memory management automatically and completely invisible to us. The garbage collection is key in memory management. A collector aims to reclaim memory occupied by objects that are no longer being used. Objects, however, that are still being referenced will not be cleaned up. We can help this garbage collector by setting the scene for it to be able to collect the objects that it requires, and by avoiding memory leaks. Memory is not required. Memory leaks is basically memory that is not required by the application any longer. However, it is still being referenced by some object, and therefore this memory can no longer be grasped by the OS. The call stack. So the call stack is a data structure that records any function calls that occur. When we call functions to execute, we're essentially pushing it onto the stack. And when we return from functions, we're essentially popping it off the stack. We can think of a stack like a Pringles container. So when you see with the Pringles container, when the Pringles get manufactured and basically packaged, you put the first Pringle that goes in is the last one that you take out and eat. The last Pringle that goes in is the first one that you take out and eat, and that's exactly what a stack is. So the first function that goes in is the last one usually to be popped. Okay. So we have access to this call stack in our console, and I'm sure all of you have seen it. It's when your JavaScript application bombs out, which is, for me, pretty often. We can step through the stack using the Chrome dev tools. When we get the error, the stack is halted, and we can essentially step through to whatever led to that error. So this is a really cool tool. It's called Loop, and it's a visualization of the runtime. It was built by a developer called Philip Roberts. So I'm going to show you how the call stack works using this tool. Okay, so I'm just going to temporarily mirror my screens. Cool. So you don't need to worry right now about the web APIs portion and the callback queue. So this is a function because we're only talking about sort of synchronous execution. So this is a function, and what it does is it composes a greeting, and then it goes. This variable isn't actually necessary, but it goes into compose greeting. It then calls say something nice. Say something nice says you guys are awesome, and then there's a console log. And that's basically what it does. So the way that I expect the call stack to basically execute this is compose greeting is the first function that it basically sees, and it puts it onto the stack. So it pushes it onto the stack. Compose greeting, then once we go into compose greeting, say something nice will get called. Once say something nice, so that gets pushed onto the stack. Once we go into say something nice, it actually returns, which means that that's our first pop from the stack. Because it's synchronous JavaScript, the next thing that gets called is console.log greeting, so that will be popped onto the stack, and it will be done with compose greeting. So this function here will then be popped off the stack. So I'm going to run it quickly, and I'm going to have to pause just as we go along because it runs very fast. So you can see compose greeting went onto the stack. Say something nice was the next thing. It went onto the stack. It will then be removed because say something nice got executed. So as soon as we return from a function, it's going to pop off the stack. The program continues executing, which is our console log. That gets pushed onto the stack, but now it will execute, so it should pop off. And finally, it will pop off compose greeting. And that's how basically synchronous functions are called, are sort of executed within the runtime environment on a call stack. So I'm just going to quickly go back to my presentation. Okay. So that was just the code that I put into Loop. So there are some errors that I've encountered that I didn't really understand what was happening behind the scenes. But now I do. The most common one is the annoying maximum call stack size exceeded. And then your browser just crashes, and it tells you that everything is just unresponsive. I think it's what Justin was talking about earlier. So what actually happens behind the scenes here? And yes, JavaScript does hate infinite loops. So when we call a function multiple times recursively, which you can see on the extreme right, function bar. So bar is being called recursively, but there's no return statement in here. So it moves into an infinite loop. So what happens when a function is called recursively? The function actually gets pushed onto the stack, but because we're not returning, nothing is getting popped off the stack. So each time the recursive call happens, it adds something to the stack, and it keeps adding things to the stack until it has a stack overflow. because our browser can essentially only have a limit on the stack size. So I think in Google Chrome, it's around 16,000 frames. And hence, Google Chrome sees that there's more than that amount of frames within your call stack, and it freaks out, and an error is thrown, and your browser starts crashing. So that's basically how that error occurs. And there's also something to note is that depending on the functions that you're executing, that's how slow or fast your stack might execute. So for example, a console log will be really snappy and quick. But something like a loop that contains multiple lines of code, that will actually take a little bit longer to execute. So since JavaScript is single-threaded, it means that the stack cannot execute and continue until a function returns a value. Imagine if we had to implement something like imagine if we had to get data from an external server and we were implementing it synchronously. What would end up happening is that network request would happen, the function would be popped onto the stack, and say if the server that we're connecting to is really, really slow, and it took 20 seconds to execute, it means that particular function would remain on the stack and not allow anything else to execute until it received that data from that external server. This would be extremely painful to everybody. And this is where we bring in Ajax. So Ajax has a callback function. And with this callback functions, with a callback function, we can essentially send it off somewhere, and once it gets its data, it then will allow it will then continue rendering. At the same time, it will allow any other functions that are rendering to continue with its execution. So when I talk about Ajax, I'm talking about things like the $get, the get timeout, the set timeout, the set interval, promises, etc. Ajax allows us to run some part of the code and then provide a callback which can execute at a later stage. The fact that there is a request and a callback and that they are completely decoupled means that we are not holding down the entire stack, but rather we are allowing the runtime to continue whilst waiting for the async function to actually get its data and complete and then fire the callback. So you'll see there's a couple of extra things. When I talked about JavaScript in a synchronous context, we only have the memory heap and the call stack. But now I've introduced 3 other components. It's the web APIs, the callback queue, and the event loop. So let's go into detail about each one of those. So web APIs essentially execute asynchronous functions. The web APIs are provided by the browsers, and they give us access to things that aren't available in the JavaScript. So things like the DOM, Ajax, timeouts, etc. So when the stack sees a function and it sees that it's asynchronous, an async event the async event will probably require one of these calls that can be provided by the web API. The browser's API kicks in, and it calls that particular element to handle it. The web API uses its internals to get what's required and then pushes the callback onto the callback queue. So essentially what the web API is doing is when you call a function in your script, and if it's asynchronous and has a callback, it actually needs to be executed by the web API. The web API then runs this portion, and once it's run, it then puts that callback onto the callback queue. So the callback queue it can be called the message queue, the callback queue, the task queue. They're all sort of used interchangeably. A message queue we can think of almost like, when you queue at ShopRite to get to the till and to pay. So it's very different from the call stack. The call stack we said is like a Pringles container, so last in, first out, whereas a message queue is first in, first out. So the oldest message on the queue will be the first one that is sent for processing. So these messages are actually queued up in response to the async events that are executed by the web APIs. The stack keeps changing, the call stack keeps changing capacity based on the functions that are executing and that are returning. So when the stack has capacity, the callback queue or the message queue essentially takes the message and it puts it onto the callback on the call stack to be able to execute. the message processing is actually calling the callback function. It ends, the message processing portion actually ends once the call stack is empty again. The runtime starts handling the messages on the queue, starting with the oldest one. Each message or callback is completely processed before a new one can actually be put onto the stack. So the event loop. When I think of the event loop, I think of the outsurance guys that stand at the robots and that direct traffic. So the event loop, essentially what it does is it looks at the call stack, it checks if the call stack is empty. If the call stack is empty, it tells the message queue or the callback queue, hey, the call stack is empty, so you can actually take a message and we can process it onto the call stack. That's what the event loop's job is. So it's responsible for the execution of the callbacks in the queue and pushing it onto the stack. So let's dive into an example with asynchronous functions in JavaScript. I'm going to use loop again just to show you the example. So just give me a second whilst I mirror my screens. Okay, so this is the default example that Philip actually puts up on his loop application. And the way this works is we have an event listener, which we know is asynchronous. And when a button is clicked, this particular button is clicked, it then goes into this function. In addition to that, we have a console log. We also have another asynchronous function, which does a set timeout. And finally, there's another console log. So the way that we expect this to work is we expect the console log to go onto the call stack, because that's synchronous. We then expect the set timeout to also go onto the call stack. But because it's asynchronous, the web API will need to give its input onto set timeout. So set timeout will then go to the web API. It will then run for 5,000 milliseconds. And then it will push that callback onto the callback queue. When it's on the callback queue, in the meantime, the console log.high, it will not stop execution. The execution will continue running. So console.log.high will be put onto the call stack. And when set timeout finally comes back, I said it would go to the callback queue. And when the stack is empty, that's the only time that the callback queue will actually put that message onto the call stack. So the way this will run, so you can see, oops. So you see in that it put the console log, it then put the set timeout, it put the on button click. It then went through the console log. It put the timeout onto the web API. The web API will then execute whatever the timeout is. It will execute. It then should go to the callback queue once it's done. The call stack we can see is empty, so it should immediately go onto the call stack. Oops, and I think, there we go. Thank God that worked. Okay. So that's basically how it works. But when we click a button, there was a point that I made earlier that said that if there is a message that is on the callback queue, another message cannot be executed and pushed to the call stack until the call stack is empty. So we see that we have two set timeouts here. The one set timeout is over here, and the other one is within the button click. So if this this bottom set timeout where it says click button is being executed and put onto the call stack, if we have to click the button whilst this is happening, it will first have to wait for this set timeout to execute before it can actually execute the callback within the button click set timeout. And one of the things that I learned over the past couple of weeks that I didn't actually realize is that when set timeout is given two arguments, the first one is the callback and the second one is the time. That time that set timeout is given is not a guaranteed time for the timer to actually run. It's the minimum time that it will be executed. It will be the minimum time that the callback can be executed. because it still needs to wait for any processing that's happening in the callback queue. So if there was a previous set timeout that was running and that took 5 seconds, and if the next one is put onto the queue and that will run in 2 seconds, it will first have to wait for the 5 seconds from the first set timeout before it can do the second one. So it has to wait for any message queues to be processed. So I'm going to go back to my presentation. Oops. Okay. That is not it. Okay. So now that we understand more about how JavaScript works under the hood, I'd like to cover how we can actually use this knowledge to optimize our code. Having this information under our belt, we are able to apply techniques to our code that sort of optimizes it for the runtime. The main aspect that you can really optimize on is the memory management. If we write code if we want to write code that ensures that we're kind of setting the scene for the garbage collector to collect all these objects instead of just leaving them lying around. So remember we said that a garbage collector is essentially aiming to reclaim memory occupied by objects that are no longer in use. So the one thing that we want to do is we want to ensure that the objects that are referenced by the app, objects that are still referenced by the app will not. So objects that are still referenced by the app will not actually be cleaned up. So we want to ensure that we remove any references to an object if it's not necessary to be global. Okay. Cool. So these are all the things that we can do in order to optimize for the runtime, and I'm going to walk through each one of them in a little bit of detail and show you examples. So the first one, scoping variables appropriately. So we all know what's global variables and what's local variables. Global variables, the way it works is that global variables are hoisted to the top whenever an application starts running. And as long as that as long as the page is open, the variable that is scoped to the global object will remain in memory. That memory will never be reallocated, and the variable will never be collected by the garbage collector. Global variables will always remain there up until you either can refresh the page or you navigate to a different page. However, when you scope something locally, and we can use now with ES6, there's lets. If you scope it locally, scoped variables are cleaned up as soon as the variable falls out of scope. So as soon as a function is exited from, or there is no longer a reference to the function, it will then fall out. It will then get cleaned up by the garbage collector. So for example, if we look at the variable value blue, that exists in the entire app. However, it's not actually necessary to exist in the entire app if you're looking on the right-hand side, because we never actually reference it anywhere else except in that if block. So instead of declaring it as a variable, the more appropriate way to be declaring it would be using let, which would only scope it to the block. Another one, and I'm really guilty of this, is unbinding event listeners when they are no longer required. So by default, event listeners will always persist after they're called. And sometimes this is necessary because if we have a button and we want to be able to keep clicking the button, it's important that that event listener is still persisting and listening out for any clicks. But for others, having an event listener persist is not always optimal. So for example, if you're loading a script in an application just once off and you want to listen for a load event, and do something once off, you don't want that event listener to persist throughout the life cycle of your application. So by default, so if we look at this function over here, this bottom one that says set up listeners, we'll see that we have variables, a variable called data, and then we have an event listener on the window that figures out that basically listens out for when it loads, and then we do something with that data. Okay. So by default, that load event listener will remain in scope when it finishes running, even though it's never used again. And because the data variable is used within that callback, that will also always remain in memory. It will both the variable data as well as the event listener will never be garbage collected. However, if the callback were removed via, if you see on top, we do a removed event listener. If it was removed via using remove event listener, or even using the once true property, which you can see in the second block, then the data variable as well as the event listener would be potential candidates for garbage collection. So cleaning up your event handlers can offer huge memory efficiency. However, some modern browsers would do the job for you. I mean, they know we are lazy human beings and we won't clean up after ourselves, so they automatically collect the observer handlers once the observed objects become unreachable, even if you forgot to remove the listener. However, in some past browsers, they were unable to handle these cases. And yes, I'm looking at you, good old Internet Explorer. So the next technique that we can use is to be able to clean up local caches or use aging mechanisms. And this is pretty simple. I mean, if you have data that you're storing locally and you no longer need it, you should probably clean it up. The way we can do that is by sort of just using some sort of aging mechanism or expiry. And depending on what you're using, you can clear up your local storage or your session storage. The next one is around closures. So when we use closures, we just need to make sure that we are accessing the variables correctly and that we don't leave variables lying around so that the garbage collector can't come in and clean it up. So if we look at this example, we'll see that we cannot access large string via A. So there's two variables, first of all. There's a variable called small string, and then there's a variable called large string. Large string isn't used in this particular program, but it's just as an example. So large string cannot be accessed via A, and hence it will be garbage collected. But because small string can be accessed via A, it will not be garbage collected. So I think the premise of this is that we should always declare our variables based on whether we actually need them to be global or whether we need them to be local within the closures. The last one is out of DOM references. These are the cases where developers store DOM references in variables. So if you look at the top, we can see a variable called elements. It contains button and image, and you can see it references the DOM. And then if we look at the bottom function, which is remove image, we can see we're going through the document body and we're removing the element image by its ID. So we've got two references to this image, right? We've got the reference in remove image, and then we've got the reference at the top in elements. So when we eventually remove the image in the function remove image, that reference in elements actually continues living on. It doesn't know that element was removed, and because it's scoped as a global variable, it will remain in memory even though it's completely unnecessary and the DOM has already removed that element. So it's important to ensure that you make both references. It's important that if you decide to get rid of a DOM element, you need to remember to make both references unreachable. Finally, chunking up work into smaller pieces. Also, so during runtime, long-running JavaScript can block the main thread, causing the pages to become unresponsive. There are certain techniques that we can use to basically chunk up the work into smaller pieces so that we don't block up the JavaScript runtime. And we can use things like request animation frame as well as request idle callback for scheduling these things on the call stack. And this can reduce any responsiveness issues. So I'm not going to say that all of you guys just go home today and rewrite all the code that you ever wrote. In fact, I'm going to say take one step at a time. If you've noticed over the past couple of months or even years that your application is running a little bit slower than you'd like it to, there are some tools out there that you can really use to identify your performance issues. So some of them, I'm a big fan of Google Chrome. So these are all Chrome dev tools, but there are equivalents in Firefox and Safari. So the first one is the timeline panel, and the timeline panel is on the extreme left. The timeline panel records and analyzes all activity in your application as it runs. It's the best place to start investigating if you have perceived performance issues. It gives you stats for things like your compile times, your parse times, and lots of data. The second one is the heap profiler, and that's basically profiles the memory distribution amongst your pages with respect to the JavaScript objects and the DOM elements. And finally, the allocation profiler, and this combines the detailed snapshot information of the heap profiler with incremental updating and tracking of the timeline panel. It uses the profile type to isolate memory leaks. By not writing code that is not optimal and performant and efficient, we run the risk of users becoming frustrated with our applications. If we have performance issues, users tend to navigate away from our application, and it directly impacts the success of our applications. It's really important for user experience. Just some stats are that 53% of users visits are abandoned if a mobile site takes more than 3 seconds to load. Personally, as a developer, I can attest to that. I think it takes me less than 3 seconds to navigate away from a page. But there's been times when I've loaded up an application and it's taken a little bit long to load, and because I have a very short attention span, I've now moved to another tab and I've completely forgotten about the window that's loading up in another tab. So it's important to have good performance on your application, and I think by leveraging our knowledge about the JavaScript engine, we can really increase the performance on applications. Another stat says that 1 out of 2 people expect a page to load in less than 2 seconds. And I hope this is the JavaScript engine after this presentation. So in conclusion, the JavaScript engine that I've walked you through is a very small part of a much, much, much bigger picture. There's so many fascinating aspects about the JavaScript engine that keeps me engaged, and so many fascinating aspects about the language that keeps me engaged. And I'm hoping that I've given you something to sort of think about for the next however long you're using JavaScript. And that, my friends, is JavaScript under the hood. Thank you very much for listening to me. I'm Ridhwana Khan, and you can follow me on Twitter with Ridhwana_K. And these are the references that I've used for my talk. Any questions?